My name is Amanda Bissett, and I'll be talking to you today about Gen 4 nuclear reactors, kind of what types there are, their goals, their differences from Gen 3 reactors, and the advantages and disadvantages of each type. So there are some shortcomings of the current nuclear reactors that we have running today that are improved with Generation 4 reactors. So Generation 4 reactors differ from a Generation 3 reactor because it takes into account at least one of the following criteria. It has increased efficiency, so it can produce more with less. It has increased safety and handling and improved waste reduction. And lastly, the heat generation from the nuclear reactor can be used in other thermal applications. So an example of this would be the production of hydrogen that can be used for various different things, such as heating and power generation for hydrogen turbines, feedstock for the production of ammonia, or it could be used for the production of hydrogen fuel. So there are many benefits to the Gen 4 reactors that show improvements from our current day Gen 3 light water reactors. So all Gen 4 reactors have two things in common. They operate at a much higher temperature, usually between 500 degrees Celsius and 1,000 degrees Celsius, compared to today's light water reactors that operate at a crispy, cool 330 degrees Celsius. So they do run quite a bit hotter. They also place much more of a burden on reaction materials than traditional systems do today. So this means that the construction material of the reactor components is a critical part of the designing process in both how they operate and what they're made of. So overall, there are four main goals of Gen 4 nuclear reactors, and we're going to start with sustainability. So with sustainability, they aim to provide sustainable energy generation that meets the clean air objectives and provides long-term availability of systems. They have effective fuel utilization processes, and they aim to minimize the waste and reduce long-term maintenance and care for the facilities. These processes in these Gen 4 reactors also occur through a closed fuel cycle so that all of the uranium and plutonium and other extremely radioactive materials are reprocessed and recycled. As far as economics are concerned, they have a clear life cycle cost advantage over other energy sources that we use today, and they have a level of financial risk that is comparable to other energy products. As far as safety and reliability, they tend to have very low likelihood and degree of reactor core damage, which eliminates the need for off-site emergency response. Lastly, they have proliferation resistance and physical protection because they're the least desirable route for theft of weapon-usable materials. So they provide an increased physical protection against acts of terrorism. Today, I'm going to be talking about the five main types of Generation 4 nuclear reactors, the molten salt reactor, the sodium-cooled fast reactor, the gas-cooled fast reactor, the lead-cooled fast reactor, and the supercritical water-cooled reactor. And I'm going to tell all about the advantages and disadvantages of each one of those reactors. So we're going to start with the advantages of the molten salt reactor. There are many advantages to the molten salt reactors, and we're going to start with fuel. Because their fuel is fluid, molten salt, it can be automatically drained into a passively cooled, critically safe dump tank where fission immediately stops in the event of a meltdown. They are excellent coolants with 25% higher volumetric heat capacity than pressurized water and 5 times that of liquid sodium, which we'll talk about later. This results in more of a compact primary loop components like pumps and heat exchangers. Stability is also a major advantage. Molten salt is very stable at high temperatures, and the fission products quickly form stable fluorides that will stay within the salt during any leak or accident. Another advantage is that they use thorium as fuel. This provides a less transuranic waste than that of a conventional reactor that we use today. And also, terrestrial thorium is 3 times as abundant as uranium. There's extremely large reserves, and even then, there was a recently new deposit found in Idaho that has added 600,000 more tons to the world reserves, increasing it by 50%. Now, only one low-pressure vessel is needed because the salts run near atmospheric pressure, so the thick-walled vessels that we have today are not necessary. These low-pressure vessels, in addition, there's no combustible material present, which means there's no possible steam explosions within the containment, which we've seen in some of the accidents with nuclear reactors in the past. Also, xenon is continuously removed, so there's no dead time after the reactor shuts down or power decreases that most solid fuel reactors deal with. So lastly, because the fissile concentrations are equally adjusted and done so on a continuous basis, there is no excess reactivity and no need for burnable poisons. Sometimes there is a control rod for shutdowns and startup, but it's not necessary given the ability to drain fuel out of the core into critically safe storage tanks. So now for the disadvantages of a molten salt reactor. The gamma rays put out by molten salt reactors required to be buried underground in order to reduce the non-necessary exposure to gamma rays. This is just the same as our light water reactors today. All nuclear waste has to be buried. They also occur in the equipment outside of the reactor, so remote maintenance is also necessary. There's also design and maintenance complications due to the presence of radioactivity. Obviously, it's a nuclear reactor, and there is a need for adequate pressure relief against a high pressure system. There's also an issue of salt cleanup problems that might occur in the event of a leakage. So more experimental work needs to be done to the design of the molten salt reactor to design a self-regulating system that's stable for constant power and also for transient and load following behavior. Moving on to sodium-cooled fast reactors and their advantages. One of the main advantages of a sodium-cooled fast reactor is their high thermal conductivity and boiling point. So this results in a couple things. One of those things is it results in a flatter radio temperature profile within the pin and a much lower normal operation and transient temperatures. This allows the reactor core to be designed with higher power density without the need to be pressurized. Another advantage to the sodium-cooled fast reactor is safety. So the coolant needed to submerge the core can be maintained without being pressurized. So again, it's that pressurization that's keeping us afloat here. They also have excellent natural circulation capacity because of their high conductivity and high system temperature difference and large temperature difference between the core inlet and the outlet coolant. The components of a sodium-cooled fast reactor have excellent compatibility with structural materials under the deoxidization condition. Corrosion and surface changes of structural materials can be controlled during the plant's lifetime by controlling and moderating concentrations of impurities. These can be hydrogen, oxygen, etc. They're also highly fuel efficient. They can extract about 2 orders of magnitude more energy from the same amount of fuel due to the closed fuel cycle. The transuranic elements that remain radioactive for a long time can be consumed by the process, significantly reducing the time period and repository space for waste isolation. So there's also some big disadvantages of sodium-cooled fast reactors, and the main concern with sodium-cooled fast reactors is safety. Although safety is a positive in that it doesn't need to be pressurized, it's also a negative in that sodium reacts extremely violently with water and air, and whenever it comes into contact with water, it produces hydrogen gas and heat, which can lead to the possibility of a fire or an explosion. They also are quite costly due to the extensive design and the corrosive nature of sodium. These lead to increased construction and maintenance costs, making more expensive than other types of reactors. Again, as we talked about with the light water reactors and all other nuclear reactors, a lot of money up front is required in order to get these things up and running. The radioactive waste generated by sodium-cooled fast reactors, they do still require careful management and disposal because of those radioactive isotopes. These include plutonium that remain hazardous for thousands of years, so they do have to be buried and taken care of that way. Being the sodium-cooled fast reactors use uranium and plutonium fuel cycles, they do have the potential to produce weapon-grade plutonium, which could be used for the production of nuclear weapons. This leads to proliferation issues, and special safety measures need to be taken in order to avoid the use of these materials for military uses or weapon uses. So the fuel of sodium-cooled fast reactors includes uranium and plutonium, which both availability and costs are an issue of concern there. So we're going to move on to gas-cooled fast reactors. These are my favorite. The gas used in gas-cooled fast reactors is helium. And a safety is a major advantage of the gas-cooled fast reactors because the reactor core is cooled by circulating gas, and this circulating gas is completely confined within the massive reactor vessels. So in the event of a rupture of pipes outside the vessel, the reactor cannot lose its primary coolant. Another very important advantage is the slow release of pressure following an interruption by some power failure, mishap, whatever it might be. So in this event, the temperature in the core releases very slowly because the fuel elements are embedded in a massive matrix of graphite. So this serves as a moderator for slowing down neutrons, as we know, and can absorb heat by fission products. In the system depressurization and total failure of the helium circulation system, more than 1 hour would be required for the temperature inside the core to reach 300 degrees. And at that temperature, both the coated fuel particles and the graphite fuel elements would not be affected. So, as a matter of fact, it can withstand temperatures greater than 4,000 degrees, and that would take more than 10 hours to heat up to that temperature, which gives emergency response teams plenty of time to take emergency measures to restore the flow of helium. Helium in the gas-cooled fast reactors is stable to the high radiation flux in the reactor and does not become radioactive. The gas itself does not become radioactive. In addition, when being compared to light water fuel reactors that we've talked about in class, gas-cooled fast reactors have better thermal efficiency, better energy utilization out of each pound of uranium. Compared to light water reactors, it releases 25% less waste heat that is dissipated into the surrounding environment. It also releases less radioactivity and at lower concentrations than a light water reactor does. And it incorporates features that ensures that the release of the radioactivity into the environment are essentially zero. So now for the disadvantages of gas-cooled fast reactors. One of the disadvantages of a gas-cooled fast reactor is its low volumetric heat capacity. This is because natural cooling is more difficult to achieve, and although natural convection can provide adequate shutdown after heating, when the coolant loop is pressurized, it usually cannot be counted on in a depressurized state shortly after shutdown. Another issue is resource limitations. Helium, again, is the gas used, is presently extracted from natural gas, which is becoming more and more limited and will continue on that trend in the future. In addition, to achieve adequate heat removal capacity with acceptable coolant pumping power requirements, it requires pressures in the range of 40 to 80 atmospheres. Lastly, due to the compressible nature of helium, the power required to operate a helium circulator can be high. So that would require 2 to 5% of the reactor's thermal power just to power the circulator itself. So we're going to move on to the advantages of lead-cooled fast reactors. So the first advantage of lead-cooled fast reactor is that lead is very dense, therefore it has excellent cooling properties. It also has high latent heat and high thermal capacities, which provide significant thermal inertia in the event of a loss of heat. In addition, there's also a simple coolant flow path and low core pressure that allows for a high level of natural circulation cooling in the primary system. Lead does not react with coolants in either water nor air, so in the event of a leakage, there will not be rapid chemical reactions like there would be with the sodium cooled. Lead also has high boiling point that allows the reactor operation at or near atmospheric pressure and eliminates the risk of core voiding due to coolant boiling. This also leads to higher safety margins and the ability to operate at higher temperatures. So an advantage to the lead-cooled fast reactors that other reactors don't have is their ability to exist in different sizes. So they have a transportable system that's 50 to 150 megawatts, a modular system that's 300 to 400 megawatts, or there's a large monolithic plant that provides more than 1,200 megawatts. So now for the disadvantages of lead-cooled fast reactors. Number one is their corrosivity. Lead is highly corrosive to structural steels. It also has high heat density and low heat conductivity that reduces the possible lead flow rates. This limits the total allowed power density and doubling time for breed plutonium. The high density and high mass of lead as a coolant causes the need for careful consideration of structural design to prevent seismic impacts on their reactor system. Also, although the high melting temperature is a positive, it's also a negative. The high melting temperature of lead requires special efforts to keep it from freezing in the primary circuit. It also poses an issue with inspection and monitoring of the reactors and core components, as well as fuel handling. In addition to these issues, lead tends to become more corrosive at high temperatures whenever it comes into contact with those structural seals, so you really have to make sure you're careful with what components you build the reactor out of. So lastly, we're going to talk about our supercritical water-cooled reactors. And one of the advantages of a supercritical water-cooled reactor is that once it's constructed, it can be easily adopted into existing systems of utilities because their evolutions of the current fleet of nuclear reactors and most utilities operate on nuclear and fossil fuel-fired power plants. They're also a relatively simple concept, which can be economically advantaged because it is water-cooled reactor. There are advantages of safeguard and proliferation resistance. The passive safety systems are good or better than existing nuclear reactors, and they have higher thermal efficiency than the current fleet of nuclear reactors. This reduces fuel utilization and waste stream, which improves the overall sustainability. And lastly, the disadvantages of supercritical water-cooled reactors. So one of the disadvantages of a supercritical water-cooled reactor is their high coolant temperature. This leads to high cladding temperature, which requires the use of stainless steel and nickel-based alloys as fuel cladding materials. In addition, refueling frequency is increased compared to today's fleet of nuclear reactors. The single-phase steam flow transport of radioactive materials from the core to the high-power turbine can hamper maintenance and inspection of the turbine and increase radioactivity dosage to staff. So the last thing with the supercritical water-cooled reactor is the fuel assemblies contain more parasitic materials than those existing reactors. So this increases waste stream. So I'll leave you with this question. Based on the Generation 4 reactors that we discussed today, which do you think is the best option for us in the future? Thank you.